This lesson deals with clipping circuits. You can find these notes in the ECE302 ebook in Chapter 2 starting on page 35. Diodes are often used to make wave shaping circuits. We'll take a look at one called a clipper. I'll break that into actually a positive clipper or a negative clipper, sometimes called limiter circuits. The circuit has an input that's not specified, so it's varying, can be any possible value. I'll treat it like a sine wave that has all possible values. Here I've got a real diode, so I'm going to replace that by our model, which is an ideal diode and a battery, VD on. Now you can put the battery first or second. Doesn't make any difference because we're going around a loop to add up voltages. You can add things in any order. Now these types of circuits, because we're not specifying V in as a value, and also not a specific value of VD on or V reference, I found the easy way to analyze these circuits is to assume that the diode is off and then solve for what V in needs to be equal to. Think of it as a resistor. You have a voltage across it from anode to cathode. The voltage across it's negative. That means the current's trying to flow in this direction, so that would be off. That implies that this node, which is the cathode, is at a higher potential than the anode. So I'm going to use that approach on these kinds of circuits. Let's start there. Let's assume that the diode D1 is off. And that means that this node voltage, which is VD on plus V reference, needs to be greater than this node voltage. But if no current flows in the diode, then the voltage across here is also zero. It's going to be this node voltage, go back to ground, minus R sub S times 0 plus VI, or just equal to VI. When this is happening, the output voltage is also that loop around here. V out is equal to minus 0 times R sub S plus V sub I, or just V sub I. The output equals the input. Now, if the diode is off when V sub I is less than VD on plus V reference, well, then it must be on when the inequality is the other way. There's only two possible states for the diode. When that's true, the diode is short, and the voltage across the output is just these two batteries. In other words, V out is equal to 0 plus VD on plus V reference. So we can show that as a picture. Here's my V sub I. I'll show it as a dotted line, a sine wave of any possible value, and here's the voltage VD on plus V reference. Whenever V in is less than that number, then the output equals the input. So I've shown this over here and back over here. But when V in is greater than this number, the output is just fixed at V out equal to VD on plus V reference. So it doesn't go anywhere, it just stops right here. In electronics, we ultimately are going to design circuits. So what I try to do is to take a circuit and describe it with a word description. We can think of this when we want to put circuits together to make a design. In fact, we'll do that in this chapter. That this circuit clips off everything above this voltage. This is what we call it a positive clipping circuit. It's like you had a pair of scissors and everything above the scissors is just cut off. We're clamping the output with that diode voltage and then the value of the reference voltage. Let's do a numerical example and then run PSpice to see how the results turn out. Let's take a 10 volt sine wave at 100 Hertz, 10 times the sine of 2 pi, 100T. Put a resistor of 1K, a reference voltage of 3 volts, and then a diode using our default values that are in our textbook of an I sub S of 2 nanoamps and an eta of 2. And whenever we write a spice file, we have a title, we have a dot end, a circuit description, and then some command lines. My voltage source is between 1 and 0. It's a sine, average value of 0, a peak of 10, and a frequency of 100. A resistor between 1 and 2 with a value of 1K. A diode between nodes 2 and 3, anode to cathode, with a model, I'll call it D mod. This is what our textbook's using. It's a diode, and then here's a value of I sub S and eta. This type of description of a PSpice file, or a spice file, is called a line editor. There is another version of PSpice and other spice simulators, what's called schematic capture, where you just click and drag parts onto the screen. The problem is that some of the parameters here are defaulted to values that might give you inaccurate results. One of those is the transient analysis line called .tran. So you start out by deciding how long you want to run the simulation. I want to run a minimum of 2 cycles to see if there's a transient response where things are changing. There's no capacitance in here, so we're going to get the same result on the second cycle we did the first, but that won't be true later in the course. The frequency is 100 Hertz, so 1 over that times 2 would be 20 milliseconds, and that would be 2 cycles. To get a smooth graph, I want to have at least 200 points. I'm going to divide that number by 200. This is called a print step. So when the program is running, it basically computes results in a print step. It takes a step, first one 0, then 100 microseconds, and so on. But there's 2 other numbers here. One is where it starts to save data. We're going to be starting at 0 where we start our problem, but later we'll see why you don't want to do that, and we'll discuss that a little bit later in the chapter. This fourth number is called the ceiling step, as it tells the program to try to speed up and run. Now, why would you do that? Well, back in the 1970s and 80s when we had mainframe computers, we paid for computing by the minute or by the second. Having a simulation run too long was going to eat up the money in your account. Sounds silly, but this is still built in. And it's defaulted to 1/50th of this number, which is 400 microseconds. In a simulation, if it's calculating a result, say, I don't know, maybe at 300 microseconds, and it finds a particular voltage or current, it then computes the next point by jumping ahead whatever the ceiling step is. So if you don't say anything here, it's going to be adding 400 microseconds to wherever you are. Now what that may do is give you a choppy looking picture in which you have a lot less points than the 200. There's a really nice example in ECE302 in the ebook in chapter 8 on pages 26 to 30 where it shows what the inaccuracies are by not specifying this. And what I'm going to do is pick the ceiling step to equal the print step. That's going to guarantee me at least 200 data points. The program also will squeeze down. So if a result starts to change between one point and another, it will also then squeeze that down to a smaller print step and then give you a more accurate result. This is like for a real fast switching waveform. Let's see what we get as a result. If I assume that the diode on voltage was 0.7, and with 3 volts here, I expect it to clip at 3.7. Let's see what it does. But I always print out the input to see if it's what I think it is. I ask for node voltage 1, and sure enough, it's a 10-volt sine wave. And you can see here one period is 10 milliseconds, and 1 over 10 milliseconds is 100 hertz. The reason I do that is sometimes I make a typing mistake and I get the wrong waveform here, and so draw a conclusion about the output that's not correct. Okay, so here's my outputs. I'm seeing them clipping, and it's at 3.7734 volts. Here at instant of time, this is the x-axis, this is the y-axis. VD on would be this number minus 3, because we had a 3-volt reference. VD on is 0.7734. Happening here is our circuit's clipping off everything above 3.7734 and literally throwing it away. If there's a positive clipper, there's probably a negative clipper. Indeed there is. Just take the diode and reverse it. Anode here, cathode here. Let's replace this real diode with an ideal diode and a battery. I'll put the battery this time on this side of the anode so that I got a series combination of these two batteries. You can put it on either side because we're adding up voltages, and you can add them up in any order. Our input is any possible input, represented by a sine wave. Reference voltage can be anything, and our VD on will be around 0.7 for silicon. We'll just leave it as a symbol. Let's use that trick we used last time of finding when this diode is off, which would mean the cathode's at a higher potential than the anode. If this was a resistor, current would be flowing in this direction, which would mean it's off. If no current is flowing, then this node voltage is minus 0 times R sub S plus V sub I. That's this equation, which is just V sub I. That needs to be greater than this node voltage, which is minus VD on plus V reference. Whenever this is true, whenever VI is greater than this number, then the diode is off. And when the diode is off, the output voltage, just go around the loop this way, is minus 0 plus V sub I, or just V sub I. If the diode is off under these conditions, then the diode must be on when the inequalities go in the other way. There's only two possible states for the diode. And that's true. The diode becomes a short. The output voltage is just equal to 0 minus VD on plus V reference. Let's sketch this again with a sine wave. Here's my input. Whenever the input is greater than this number, the output equals the input. And whenever the input is less than this number, then the output is just a constant of minus VD on plus V reference. Describing this circuit as a word description, so we can use it for designing, is that this circuit clips off everything below this voltage. It's like, again, having a pair of scissors where everything below the scissors is cut off. Back to the top here. When this diode is on, current's flowing in this direction, and this reference voltage is generating power. In our previous case of the positive clipper, the opposite was true. The current was flowing in this direction when the diode was on. We'll later look in the chapter for things called Zener diodes, which can create reference voltages, but they can only absorb power. If the reference voltage is positive in these two circuits, this one would need to be able to generate power. We'll look at an example in a little bit about this. Let's repeat our last example with a 6-volt reference and just flip the diode. Here we have a title for our file, a dot end, a circuit description, and then some command lines. Again, I'll use the same numbers here where I've got 2 cycles I'm plotting, a print step of at least 200 data points, and then a ceiling step of 200 data points. If we assume that VD on is 0.7, then I would expect the clipping to occur at 6 volts minus 0.7 or 5.3. So let's see what happens. Input's still a sine wave. Here's my output. I'm clipping off everything below my reference voltage minus VD on. I assumed it was 0.7, but let's use this number here to see what it is. So 6 volts minus VD on. This case is equal to 5.1805. If I solve for VD on, I get 0.8195. So our value of the diode drop depends on the value of 8 in isobest and how much current's flowing through it. Here we've got a little larger battery and some more current's flowing. I'm getting a bigger drop across the diode when the diode's conducting, which is going on here. Now both of these clippers can actually have negative reference voltages, and let me show you another example. Let's take a look at what's called a double clipper. Let's take our positive clipper with a positive reference voltage, and now let's take our negative clipper, but let's make the reference voltage negative. So you can figure out what's going on here. Let's replace the diode by an ideal diode and a battery. Likewise here, a battery and an ideal diode. So I got these batteries in series. Let's figure out how this thing works. If the input were positive, then current would want to flow in this direction and this direction, but current can't flow this way. So when this is big enough, current will flow this way, and the output will be 0 volts plus VD on plus V1. So we're going to clip the positive portion here at VD on plus V1. When the input goes negative, current can flow this way, but it can't flow this way. So when this is negative enough, this will conduct, and the output voltage will be equal to minus 0, minus VD on, minus V2. So here we got a negative reference voltage. We're going to clip everything below the waveform here. So we're clipping the top off or clipping off the bottom. What's interesting here, though, is when this diode is conducting, this reference voltage is absorbing power. And when this diode is conducting, this reference voltage is absorbing power. So we'll be able to put in here what are called Zener diodes. These are diodes that can create a reference voltage, but they can only absorb power. Who would use a circuit like this? Well, to protect an output. Suppose you had a speaker here, and this represented the most power you could put into the speaker. In other words, the voltage was high enough that that voltage would be at the rating of the speaker. And likewise down over here. That when the input increased and the output started to increase, we would stop it from getting any bigger than a particular value to protect the speaker. It would distort the sound, but it wouldn't destroy the speaker. Let's verify this with PSpice. I would expect the clipping to be at 5.7 and minus 5.7 if the drop across the diode was 0.7. Let's see what it does. I have my 10 volt, 100 hertz sine wave. I'm clipping at 5.7536 and minus 5.7536. My voltage across the diode is subtracting 5 from that number, which is 0.7536. And these are clipping circuits.